Okay, welcome everyone to this morning's session. It's a pleasure to have Karen Vogtmann be talking about graph complexes.
Thank you. As usual, like everybody else, I really appreciate the invitation to speak here, and thank you to the organizers for organizing this. I have to talk to the people in the very back of the room. If you have trouble hearing me, please let me know. There is a microphone available. It's okay? Okay, good. Okay, so what do I want to talk about? Graph complexes. So this is kind of the outline of what I would like to talk about during these 2 hours. First is graph. There's various types of graph complexes, what they are. I'm going to spend time defining them and giving you some examples. And then after I talk about these complexes, I want to talk about spaces of graphs. So those are the names of some of the spaces I want to talk about. And then I want to relate the 2 graph complexes and the spaces of graphs, in particular in terms of cohomology. And then finally, we'll talk about some calculations and some applications. So that's the plan. So let's get started. So I should first give the origin story. Where do graph complexes come from? So there are 2, Kontsevich in the early 90s wrote 2 articles, Feynman diagrams in low-dimensional topology and formal non-commutative symplectic geometry. And in these papers, he was interested in, he introduced graph complexes in these papers. And but what he was doing was studying deformation quantization in physics. So I don't pretend to understand any of the physics behind deformation quantization. What I do understand is the idea is you've got some physical system with phase space, which is a symplectic manifold, and there's a Poisson bracket. On the commutative algebra, there's some functions on this manifold. And that's what you'd like to study, but it's hard. And what you do when you quantize something is you think of that as a deformation of the thing you were studying, and you replace this commutative algebra with a non-commutative algebra, the formal power series. So the formal power series in some variable, which is usually thought of as Planck's constant, H. So formal power series in H. And it's got this power series has a star operator on it, which when you go to H equals 0, you get the Poisson back bracket and the original commutative. So that's a deformation of the original algebra. That's what he wanted to study, and graph complexes came up naturally while studying this situation. And then he found connections between this graph homology that he invented and various things in low-dimensional topology. That's the name of the first paper. In particular, they're related to the cohomology of configuration spaces of points on a manifold, these manifolds and manifold. They contain, graph homology complexes contain invariants of homology 3 spheres, and they're closely related to various not invariants, like the Celia invariants, you know what those are. Then in the second paper, actually, already in the first paper, actually, he generalized this whole picture of how these graph complexes are related to these deformation algebras from commutative algebras, which he started with, to associative and Lie algebras. So he had this formalism about deformation quantization, and he generalized it, as I said, And when he did that, he found that there are connections with mapping class groups of function surfaces and outer automorphisms of free groups. So that's the motivation. That's where these things come from. So it's all very esoteric, I guess. But when you get down to what a graph complex actually is, it's really a very simple combinatorial object. So we're going to start with some combinatorics, and maybe later we'll try to understand how it's related to some of these other things. Right, so what's a graph complex? Well, throughout the entire 2 hours this morning, we're going to have a fixed field of characteristic 0. And in fact, I'll probably take it the real numbers. So all vector spaces are real vector spaces. All homology groups are homology with coefficients in R. And what's the idea? What's a graph complex? Well, a graph complex is a chain complex. So a bunch of vector spaces with their differentials D, or boundary, where the kth guy in the kth vector space in the chain complex is generated by isomorphism classes of finite connected graphs with k vertices, and all of the vertices have to be at least trivalent. So by a graph, I mean something as in this picture down here, where blue dots with vertices, I've got edges, I've got multiple edges between, I could have multiple edges between vertices, and I can have loops at vertices. And I want a boundary op, so that's a generator of chains. That's a generator of C4 on my picture. And the boundary operator, what I want it to do is to take a K chain and take a graph like this and take an edge that's not a loop, that's E, and contract that edge to get a new graph. So if I contract that edge, I get 3 vertices instead of 4, and the red edge becomes just a red dot. So this is a picture of G sub E. And I want to define the boundary operator by saying just take all the edges that aren't loops, contract them one at a time, and add them up. Okay? But there's a problem with that. I need to get a chain complex, I need boundary equal to 0, right? So I have no way of saying how to add graphs, how to get boundary equal to 0. So I'm going to fix that. So I repeated the problem up there. I need the boundary squared equal to 0, and here's a solution. I orient the graphs, and then I take G with one orientation to be equal to minus G with the opposite orientation. So how do I orient the graphs? Well, one way is just order, just graph up to even orientation. So I can do, say, 1, 2, 3, 4, 5, 6, 7. So that's an orientation on this graph, and I want to say it's the same as, well, let's do an even permutation of the numbers here. See if I can do this in real time. 7, 2, that's an odd permutation. And if I do another one, say, that's an even permutation. Okay, so a graph has 2 permutations. So another way to say this is if you've got n edges in the graph, an orientation is a unit vector in the wedge product lambda n of r to the n. which is a one-dimensional vector space. So, right, I have, yeah. So I've got 7 edges here, and I would call this E1 wedge E7. And here I've switched some. I've done 2 transpositions, so yeah, I get the same wedge product, the same unit vector. Okay, and then I define G with a given orientation to be minus G with the opposite orientation. So that's good. Remember, I wanted my boundary operator to collapse all the edges. So how do I do that? So in order to do that, I'm going to need an induced orientation on the graph when I collapse an edge. So here's my edge. E. I've got some numbering. I forget what I have. 1, 2, 3, 4, 5, 6, 7, 8. I don't have 8 edges. I only have 7 edges. 1, 2, 3, 4, 5, 6, 7. Okay, so now I need an orientation on that. So I choose a representative of the orientation with my edge to be the last guy in the orientation. I didn't do very well here. I want E to be number 7. There. Now I use the last one in the orientation, and then I just collapse that edge, and I have 1, 2, 3, 4, 5, 6. That's an orientation on GCD. Okay. So yeah. And I call that orientation on G sub E, I call that induced orientation. Or E. And then I just define the boundary to be the sum of all non-loop edges, G sub E or C. And for those of you who are bored, you can do the exercise, the boundary squared is equal to 0 now. Try a graph with 3 vertices. Okay, so that's a way to get it. So that gives me a way, a chain complex, and that's a graph complex. However, it's not the only way to orient a graph, to associate an orientation on the graph. Here's another way. It looks a little more complicated. I'm going to order the vertices. And I'm going to orient the edges. Okay. And I'm going to say, in order to change the orientation to its opposite, either I switch an arrow on the edges, or I do an even permutation of the vertex limits. Okay. Those are 2 ways to change the orientation to the opposite orientation. So in terms of, in the algebraic way of saying this, an orientation is a unit vector in the following one-dimensional vector space. Determinant of R to the V of G, that just orders the vertices. And then for each edge, I'm going to take R to the H of E, where H of E is the number of half edges of E. So if I order the half edges of an edge, that's the same as putting an arrow on the edge. Okay, so yeah, that says exactly the same thing as my picture up there. Okay, and again, I want to use this orientation to define a boundary operator with boundary squared equal to 0. So to orient this, I choose some representative of the orientation on G so that E is so that the endpoints of E are ordered, are labeled n-1 and n, and E is oriented in the direction from n to n-1, and then I just collapse E, and I get a local picture. Yeah. Yeah, so I was gonna do this in real time too. 1 to 3. 1, 4 to 2. That's the same orientation. I just did an even oriented permutation of the vertices, and my edge is oriented in the right direction. So now when I collapse it, I just get this orientation. Okay. So is that clear? And now I define the boundary by adding up over all nominal edges G sub E, with its induced orientation for sub E. And again, second exercise, just like the first exercise, this really does give me a chain complex, and squared is equal to 0. So these are the simplest two graph complexes. Both of these orientations are natural in different contexts. The first one is called an even orientation, and the second one is called an odd orientation, depending on which paper you read of Kontsevich, which makes it very confusing. But it's kind of settled down these days. Right. Where the even one, yeah, the first one is called the even one, and the second one is called the odd one. That's what I said, I think. Okay, so now just define the graph complex to be the vector space generated by oriented admissible graphs, modulo G or is minus G minus or, and admissible means, as I said in the very beginning, my graphs are finite graphs. They're connected. All vertices have valence at least 3. And right. So that gives us a chain complex of graphs. So when you have a chain complex, you can take its homology, parallel boundary modulo image of boundary. So that gives you even and odd graph homology. And one thing to notice about this whole concept is if you look at the Euler characteristic of the graph, the vertices minus the edges, then doing an edge collapse doesn't change that. It decreases the number of edges by 1, and it decreases the number of vertices by 1. So the Euler characteristic doesn't change. So in fact, this whole graph complex, both the even and the odd ones, actually decompose into a direct sum of chain complexes, one for each Euler characteristic. Okay. Now, a couple of remarks about this construction. If you have an even orientation, if a graph has a multiple edge, then it's 0 in the chain complex. Why is that? Well, if I have a multiple edge and I put the 1 and 2 on the, label the edges 1 and 2 and do a transposition, I'm supposed to get a minus sign. But this graph, so what did I say? What did I mean about generated by graphs? What I meant is it's generated by isomorphism classes of graphs. If graphs are isomorphic, they're the same graph. So the graph on the left is isomorphic. The graph, the middle graph there is isomorphic to the right-hand graph. I can see an automorphism of the graph that just flips those two edges. And that gives me an isomorphism of the two graphs. Preserves the labelings on the edges. Okay, so 1, 2 is isomorphic to its negative. It's equal to its negative in the graph complex. So that means it's equal to 0. With the odd orientation, on the other hand, if the graph is a loop, then it has to be 0 in the graph complex, because if I take my loop and I switch the arrow, this was going this way, whoops. This one was going this way, and I switch it to going this way, I get a minus sign, but there's a graph isomorphism between that graph and that graph. Then we just put the edge. So I can either flip the arrow or flip the edge. And so I get this graph is equal to its negative.
If you want an isomorphism that preserves the orientation.
If I have an isomorphism, then it's an isomorphism.
Yeah, I just say it's unusual definition of graphs of orientation, but you don't require the isomorphism to preserve
No, no.
that.
The graph is just a graph up to isomorphism. Right. And then here's an exercise with either orientation. This graph, the square graph, is equal to 0. And another good exercise. This is supposed to be a workshop, right? You guys are supposed to work. If you have the even orientation, any graph with the property that every edge is in a triangle is a cycle. This is an easy exercise. Collapse an edge in a triangle, and then you get a double edge, which is 0. Okay. So here's some examples, some very important examples of finite graphs, finite admissible graphs, where every edge is in a triangle. And these particular graphs are called odd wheels, and they represent cycles in the even graph homology, even graph complex.
So even orientation vanishes whenever you have an involution that changes an even number of that adds on even number of pairs.
In the even graph complex, right? In the odd graph complex, you need a graph automorphism that changes the orientations to its negative, right? So that's the most basic graph complex. That's really the first one that Kontsevich studied, and he originally called that just plain graph homology. But there are lots of variations that turn out to be very useful. There are hairy graph complexes. So here again, I've got the same sort of idea. All the vertices have to be trivalent, but we're going to allow pairs. So we don't think of the ends of the hairs as vertices. We think of those as basically half edges sticking out of the graph. And you can label the hairs. Got S hairs, you label them one on the S. And then the symmetric group acts on the labels, and the orbits are hairy unlabeled graphs. So there's a complex of hairy labeled graphs and a complex of hairy unlabeled graphs. When you form the boundary operator, only the interior edges are contracted. You don't contract the release. I think by my computations, I'm not going to have time to say much about this and how, but well, let me just say one thing. Supposing you have a graph. Oops. Yeah, the graph. I shouldn't have done this. I should have just why am I having such a hard time swiping? Yeah, supposing I have a graph which it has some vertices, some edges. So, something like that. And I'm interested in understanding something about this complex of graphs. Well, I can take a graph and cut it into pieces. Maybe cut there and there. Physicists like to do this. They call them Cosby cuts. And then what I get is two graphs with pairs. And I've cut my graph into two pieces. So I can assemble graphs with two pieces into graphs. I can assemble graphs with pairs into graphs without pairs. This is reflected on the level of graph complexes, and in fact, on the level of graph homology. And it turns out if you can find homology in these hairy graph pieces, hairy graph homologies, you can stick the hairs together and hope to get classes in the homology of the graph complex. That's probably all I will say about hairy graph complexes. But I do want to say something about O-graph complexes. So it turns out you can do this whole picture starting with any cyclic operatic. And the idea is to have this graph with its orientation, even or odd, whichever you like. And at each vertex of the graph, you stick in a generator of your cyclic operatic. And then edge collapse is combined with operatic composition to form the boundary operator. So I'll say a little bit more about that in a minute, but I guess in this conference, most people are familiar with operatics, but just in case you aren't, I'm going to give you a very hand-wavy idea of what an operatic is. So yeah, here's my definition of operatic. It's a black box, and it's got some input slots and an output slot. And you can plug the output slot of any, well, this is a generator of the operatic. You can plug the output slot into an input slot of another generator to produce a new generator. That's the operation in the operatic, and the symmetric group acts on the input slots. And the difference between an operatic and a cyclic operatic is that the action of the symmetric group on the input slots extends to the whole, to sigma k plus 1, which you can think of as just saying that any of these slots could be the output slot. So let me do the only examples I'll talk about in this talk are the ones that Kontsevich considered in his papers that I wrote up at the beginning. There was the commutative operatic, the associative operatic, and I don't want to hide that one, the Lie operatic. For those, what's inside the black box? The commutative operatic, well, there's nothing inside the black box. It's just a bunch of slots. The idea is if I put some things in these slots, I get an output, and it doesn't matter which order I put them in, I get the same output. I can switch them around however I want. That's commutative. So commutative operatic models commutative algebras. The associative operatic, what I put in the black box, is also a graph, but it's got a cyclic order to it. So when I put things into the input slots, they come out the output slot, and it does matter which order I put them in. So that's why I've got a cyclic order, A, B, C, D, E. I can associate them any way I want, but I can't change their order. So that's the associative operatic. It models associative operations in algebras. And then there's the Lie operatic. What goes in the black box is a trivalent planar tree. The fact that it's planar tree is indicated by putting little circles around these things. Okay, and if I put things in the input slots, then yeah, it's no longer associative. It does matter which things I do operate first. First, I have to do CD. Then I have to do the result of that with B. Then I have to do the result of that with A in this picture. Okay, so those are just the pictures that model the operands. So I'm supposed to make a complex by replacing each vertex in my graph by one of these pictures. Either nothing, it's a vertex, it's just a vertex, or it's a vertex with cyclic ordering around the edges, or it's a little trivalent tree, standard trivalent tree. So I decorate my vertices with these things, and then what does edge collapse do? Well, in the commutative case, edge collapse does just exactly what I did before. I just collapse the edge. That's fine. In the associative class case, I want to choose the orientations to be coherent at the two vertices. So I might have to change the sign of the thing. And then when they're coherent, I can collapse the edge, and the cyclic ordering around this one and this one merge into the cyclic ordering around the whole thing. And for the Lie case, well, I have these two little trivalent trees. I just have an edge. I just stick them together and get a bigger trivalent tree. So that's what edge collapse is. And that allows me to make these decorated graphs into a complex. The boundary of G is just going to be the boundary. I can't get rid of myself, but
you may be able to slide it off the screen and you keep going with this.
oh, what do you know? Okay, so the boundary is just the sum of the collapsed guys. Again, we still have oriented graphs, so we call this orientation data on graphs. And I have an even version and an odd version. I have to say that the Lie operand requires a little more explanation than that. Because one of my little rooted trivalent trees is decorating the vertex of one of my graphs. Well, how is that associated? Why is that associated to Lie, a Lie operation? The idea is that shows me a bracket expression like that. And in a Lie algebra, brackets obey the Jacobi identity. And if you do graph homology, then instead of writing this, the Jacobi identity like this, you write it like this. So all I've done is smush the pictures around. And instead of a Jacobi relation, it's called an IHX relation, because the guy on the left looks like an I. The guy in the middle looks like an H, and the guy on the right looks like an X. Oops, yeah, anyway. So IHX is just code word for, you see this in stuff, it's a code word for the Jacobi identity. Okay, so since Lie algebras satisfy the Jacobi identity, when I make this graph complex, oh yeah, and then what's different in the cyclic version, any leaf could be the root. So instead of putting a little dot to indicate it's the root, I'll give it a letter E, and to indicate that anything could be the root, I'll just draw it like that. So if I want D to be the root, I would, what would I do? Okay. I don't know what I would do, A, B, C. Right, if I wanted to be. Okay, so, anyway, it can be the root, and, the graph complex is generated by these Lie graphs. Thought of without, cyclically like this. This is a Lie graph. This is a little piece of a Lie graph. Where I should think of all these letters as corresponding to the rest of the graph, pieces of the rest of the graph. And the IHX relations take an internal edge, like this green one, and do an IH, like this green one here, and do an IHX relation on it. So that minus that plus that is supposed to be equal to 0. So in the graph complex, these things that I've called Lie graphs don't actually form a basis for the chains, because there's a relation, namely the IHX relation. So the Lie graph complex is a little more complicated than the commutative or associative graph complex, but it's still the same idea. You stick an operand generator into each vertex of the graph. Yeah. So let me point out that an odd Lie graph is a complicated looking object. Okay, so I have a graph. Let's do the odd orientation. So I've got arrows on all these edges. I've got an ordering of the vertices. And in each vertex, I've plugged in a little Lie graph. So these are planar. These are planar, so I've got little orientations around all these guys. So that they stay in the plane, don't jump out of it. Okay, so that's a picture of a Lie graph. And then, of course, I have to line out my IHX relations. But here's a proposition that Jim Conant and I proved that this is a Lie graph with the odd orientation. I claim it's equivalent to just a pair consisting of a trivalent graph and a spanning forest. So in this picture, what have I got? Where's my trivalent graph? Well, take the little graphs inside the circles and forget the circles. Can I do this? Let's see. I don't know how to convert that to text. That would be an interesting exercise. Okay, so forget the little circles. Forget the little circles. Forget the little circles. Forget, right now I'm supposed to have, so there I have a trivalent graph. Where's my spanning forest? Well, I just take all the edges that used to be in the Lie graphs. So there's that edge, that edge, that edge, and that edge. There's a forest. It's a spanning forest. It includes every single vertex of my graph. Whoops, that's not a spanning forest, right? Contains every vertex. I'm sorry. I'm not used to doing this, and here we go. Got all the vertices, right? 1, 2. That's a spanning forest. It's got 3 edges. Okay? And all I have to do, and forget the ordering on the vertices. And forget the orientations on the edges. It's looking simpler and simpler and simpler. But I do have to have some orientation data, and the only orientation I need is an ordering on the edges in the forest. Okay? So all of that data over there is equivalent to that picture. I don't know whether I've got the orientation or the negative orientation. And actually, this proposition, I don't know if a simple combinatorial proves that these orientations match. You use the algebraic definition of what the orientation is a unit vector and some tensor product. And you do a bunch of exact sequences and stuff, and it turns out that it's equivalent to this.
Does equivalent mean here?
Sorry?
Does equivalent mean here? They're clearly different thingies.
They're
So you
different
get
things.
one, a third.
Right, okay, right. But I'm saying every orientation over that, like that, corresponds to an orientation over that, so.
So you can
What-
reconstruct.
Well, so what I would like is some easy way to see that if I say switch an arrow over there, it switches the orientation over here. Which is not at all obvious, I don't think. Right, and so then what does the boundary map do? Well, before, what did the boundary map do? You took an edge and you collapsed it. But collapsing it just melded these 2 trees, and the result was a bigger tree. That those 2 vertices became that vertex, and so what's happening over here is just I'm adding an edge to the forest. So the boundary map just adds an edge to the forest in all possible ways and adds. And you can put the edge as the last edge of the forest, and that makes all of the numbers work out. The boundary square equal to 0. Okay, so this is supposed to convince you that this Lie graph complex is not quite as complicated as it might seem. It's just a generator is a pair consisting of a graph and a forest in the graph. And then, of course, you have to mod out by IHX relations. Okay. So now we have chain complexes. But if you're a low-dimensional topologist, you like to think of a chain complex as a chain complex for some topological space. Yeah, if you're an algebraic topologist, I guess you kind of move right away from that. But a low-dimensional topologist really likes to keep spaces in mind. So what I want to do now is show how you can interpret these chain complexes, Kontsevich complexes, as chain complexes for some topological structures. So I've got a chain complex of graphs, so it makes sense that what I want to do is look for some space of graphs. But how do I make graphs into a space? Well, the idea is to think of them, put metrics on them. And then to make a space of graphs, what you do is let the metrics vary continuously, and then that moves you around in the space. That's the idea. So let me make that more precise. So what is a metric graph? I take a graph, one of my invisible graphs, say, and I put a positive real number on every edge. I think of that as the length of the edge. And then I get a path metric on the graph. So the distance, I think of this as an interval of length 1. And to get and this is, whoops. an interval length 1, this is an interval length a half over here. Yeah. And if I want to get from a point on this edge to a point on this edge, well, I've got a choice of possible paths. I either have this path or the other path, go be crazy and go all around the path. But the distance between those 2 points is the length of the shortest path. So it's whatever this distance is plus this distance. Okay, so I can make a graph into a metric space. Right. So remember the graphs we've talked about so far, they're all admissible, which means they're not random graphs. It means they're finite, they're connected, all vertices have valence at least 3. Notice if I'm thinking of metric graphs, then vertices of valence 2 don't do anything at all for me. Doesn't change the metric on the graph at all. So, yeah, maybe we'll just leave them out. Right, so those are metric graphs, and how do I make a space? Well, I consider this is a space called outer space. So the points are consist of an invisible metric graph, but each of these graphs has a marking, and there's an equivalence relation. So a marking is an isomorphism between the free group on rank n and the fundamental group of the graph. Now, notice I haven't chosen base points on my graphs. So this isomorphism is only well defined up to inner automorphism. Okay, and my graphs, if one graph is isometric to another graph, I think of that as the same graph. So this equivalence relation I've written over here is, well, there's two equivalences. Conjugation in Fn, in other words, the inner automorphism of Fn doesn't change anything. And isometries of G don't change anything. Okay, so that's a point in this space. And right. And then I get an action of the group of outer automorphisms of the free group, which just changes the marking. So if I've got an outer automorphism, I just change that. So G acted on the right by phi is G composed with phi. Same graph, different isomorphism. So the stabilizer of a point is just the group of isometries of the graph. Okay, so that's outer space. But there's a way to think it, so it's, well, that's the points in outer space. What's the topology in outer space? Well, as I said, you move around outer space by varying the lengths of edges. So if I have, and what I want to do to make nice pictures is to normalize so the sum of the lengths is equal to 1. I'm not going to put this somewhere else. Yeah, I want the sum of the lengths of each of the 1. So 1/2, 1/4, 1/4. That's the point in this open simplex. And altogether, if the sum of the lengths is equal to 1, then I get a simplex, which I'm going to call sigma of G. So everything in the interior of that simplex corresponds to a graph like that, but the lengths are different and they sum to 1. And then the whole space is the union of these open simplices modulo face relations. So what are the face relations? Well, in the middle here, I have the simplex sigma of that with some marking. The marking is indicated, we say F2 is XY. And I'm making X go around the left-hand loop and Y go around the right-hand loop. You can have much more complicated markings where X goes 47 times around Y. And Y goes once around Y, for instance. But this is sigma of this G with G marking indicated. And this is sigma of this with a marking. And if I just collapse the middle edge, I get that picture. Incidentally, this graph is the same as this graph because there's an isometry to it. The only difference between those two pictures of roses is the Y is going in the opposite direction. And so that's isometry of the graph. And so it's the same point. Anyway, if I collapse that green edge, I get that. If I collapse, actually, it looks like it kind of goes to that picture. So I collapse the green edge over here. I go to that picture, but that's the same point. So the whole thing gets glued. Yeah. You get the idea. Yeah, it's good. Okay. And so you can do this. There's lots of ways to mark the graph, infinitely many ways. You can see some of them in this picture. There's a marking that's doesn't look like that. There's only two graphs with that are admissible with fundamental group L2. There's the one I've drawn a lot of. And there's three graphs. There's that one, and there's that one. And so they're all in this picture. I have a union of open syntheses. And the theorem, which was proved in ancient times, is that this is a contractible space and this action is proper. And the quotient, so if you have a contractible space and a proper action in a discrete group, then you know that the quotient is has the same rational homology or real homology as the quotient space. So you can actually use this to compute the cohomology of out of Fn. Yeah. So I want to emphasize the fact here that CDN only, a lot of points in this picture are missing. Because for every graph I had an open simplex. And I was gluing them together if I could collapse something and get the same thing. But that when I collapse something, I still had to have the graph with fundamental group Fn. If I collapse a loop, that's not going to happen. So, for instance, in this picture, I can collapse any one of the three edges and get a rose. But if I collapse two of the edges, I would go to a corner of this picture. And that collapses in. So it's not actually in my space. So sigma of GG is just the open simplex. Some of its spaces are there and some of its spaces aren't. Right. So one way to fix this is take what's called a simplicial closure. CDN is a disjoint union of these open spaces modulating space relations. But I can just take the disjoint union, I can just close up all the syntheses and line out by face relations, in which case all this stuff, all this red stuff Notice incidentally, for these guys, only one face is actually in it, CDN. Because if I collapse anything other than the middle edge I collapse, I get a perfectly good graph, but if I collapse any of the other edges, any of the pair of edges, I kill some fundamental group. I can't do that. So that red part is not in CDN, but it is in CDN star. So all this red stuff is in CDN star, but it's not in CDN. And I define CBN infinity to be CBN star minus CBN. So that's the stuff in infinity. Spaces of graphs. So those are two spaces of graphs. One more space, and then I'll stop. Yeah. CBN contains, so the quotient by the action is not compact. That's basically due to the fact that all these simplices are missing. The simplices have faces that are missing. If you take this simplicial closure, the quotient is compact, but the action is no longer proper. So what you really like to have is a proper and co-compact action, especially if you're a geometric group theorist. And any of those here. Okay. So if you have a proper co-compact action, then the space is actually quasi-isometric to the group. And the geometry of the space, the coarse geometry of the space is related to the coarse geometry of the group. Anyway, we're doing algebraic topology today. So what is this spine? How do you get it? Well, you take the barycentric subdivision of the simplicial closure. So all these simplices get barycentrically subdivided. And then you, some of the vertices of the barycentric subdivision are actually in the space. Mainly these. Some of them aren't in the space, same with the corners of the triangles, and we take the subcomplex span by all of these guys. And you get a deformation retract from CBN to CBN to the spine by just pushing in from the missing faces towards the faces that are there. And as I said, the advantage of this is that it's sitting inside of that space. So the action restricts. This is also the geometric realization of the partially ordered set of the sigma of GGs. The action restricts, and the quotient is compact. So it makes geometric group theorists happy. A picture in the whole space. Yeah, I just got 1 minute. I'll just draw pictures. Yeah, so we have this. And then there's that. Oops, did I get this wrong? Yes, I did this wrong. I'm sorry. Those points are actually not in outer space, right? This was this red stuff at infinity. All right, right. So I just have this little edge sticking up there. Or if I'm looking down from, infinity, from way up top, all those fins, those yellow fins are, I can't see them, they're straight up, and the spine just looks like this. Which some of you might know as the tree for SL2Z, which is not surprising because, well, out of the, it's actually isomorphic to GL2Z. Yeah, so this is the picture of the spine of outer space, and see, oh yeah. Yeah, so that's probably enough. Yeah, it's 10:30. I'll stop.
Thanks very much. Question for the speaker?
In your definition of the complexes, we can realize the vertices by simply pairs. Can we,
Sorry.
we can realize the vertices by simply pairs. Can we do the same with vertices?
Anti-secret operators, I don't know what that is.
It's very specific about that the action of the identity is the signature instead of the identity.
Oh, yes, yes, absolutely. So that gives you from the even version to the odd version of the graph. I didn't know the terminology, yes.
Further questions?
If you override these relations, IH these relations, we could have them to model them out by hand, or do they already follow their own? I didn't understand that.
Sorry, I'm having trouble here.
So you have these IH relations.
Right, with the secret one.
Yeah. Do you have to model them out by hand, or are they killed by some other relations?
Modern out by hand.
By hand. I mean, you have to say, I take a quotient
Yeah.
So you have to redo this. This doesn't happen on its own.
Well, you have to interpret it somehow. Yes, it's not fair on the so.
I see. Yeah.
Yeah, so I'll come back next hour and I'll straighten it out.
Okay.
So this beautiful picture here suggests some connection to hyperbolic geometry and also the GL2.
That would be nice. So you can prove that there's no hyperbolic metric on outer space. In fact, there's no cat zero metric on outer space, or, well, actually, no, that's not true. There's no, you can't put a cat zero metric on its spine. Possibly you could put a cat, no, I think nobody knows when you could put a cat zero metric, sort of similar to the Vogtmann metric on entire atmosphere. The only natural metric that's invariant under the action out of the fan that we know is a non-symmetric metric. It's a Fisher metric. So, and it's useful, but yeah. Yeah, no, there are lots of problems with outer space that you don't see for outer, for say, nothing about tabular space or symmetric spaces. And the main one is that it's not a manifold, as you can see from that picture. But even more in dimensions, it's not a manifold. All the tools that you love for manifolds, like point radiality, well, especially point radiality, are not available. So you have to invent other ways of doing things.
All right, there are no further questions, and let's thank the speaker again.